So we've got another problem. This time, guy's not so fast, right? Last time the guy was going 30 feet per second. This time, waddling along a little more slow, 20 feet per second. A little longer jump. It's 15 feet now that he's got to make, but the next rooftop's a little lower. That rooftop being lower means we're going to attack the problem in a little different way. I'm still going to do the same steps. I'm going to resolve the vector number 1. Good idea to pause me and work ahead on that. Otherwise, we'll go ahead and resolve it together pretty quick. I'm going to go 20 feet per second. You can't resolve it because I didn't pick an angle. Let's go 20 degrees again. 20 feet per second times cosine of 20 would give us our Vx. And our Vy would be 20 feet per second times sine of 20 degrees. Right? Let's not make those hard. Just get used to those enough that you can just do those, right? So 20 cosine 20, my velocity in the x direction is 19 feet per second. Whoops, I got my colors mixed up. And 20 sine of 20 is going to be 6.8 feet per second in the y direction and in the x direction. So what we normally do is we typically use the y direction to solve for time because it goes up and back down at the same speed that it comes up at. But he's not going to land at the same height. He's going to land down lower. So if he's going to land down lower, that's not how fast he's going up and down is going to dictate how long he's in the air. How long he needs to be in the air to clear this will be dictated by the x. So we're going to say, well, if he's going 19 feet per second, 19 feet per second times his time needs to equal 15 feet. This would be the time. This is not going to tell us how long he's actually in the air. This is going to tell us how long he would need to be in the air to get to this point, right? Kind of like the field goal problem we did in class. So 15 divided by 19 means he needs to be in the air for 0.8 seconds to get to that other side. That's how long he needs to be in the air. If we deal with our y side now, again, feel free to pause me and work ahead if you think you might know what to do. If we want to deal with our y side now, he's going to go up and down here. We need to know what his height is at that 0.8 seconds. So maybe his height is up here and he's fine. Maybe his height is down here. But if his height is less than negative 10 feet, then he won't have made it. So all we have to do is plug that time in and say, well, what's our y height if our initial velocity times time plus 1/2 at squared? So we say, well, his initial velocity was 6.8 feet per second times 0.8 seconds plus what gravity does to us times that time squared. So it says 6.8 feet per second times 0.8 seconds plus 1/2 of negative 32 times 0.8. Right, so that's going to tell us how far we go. So 6.8 times 0.8 tells us, very helpful.
Students, this is a cold yellow drill.
I don't care.
Students, this is a cold yellow drill.
So the 5.4 feet is how far up he would have gone if there was no gravity, right? He would have gone up 5.4 feet right here and ended up 5.4 feet higher than this thing if there was no gravity. There is gravity, so we would say plus negative 16 times 0.8 squared gives us a negative 10.2 feet. So he is below where he originally started because he went up 5.4 feet, would have gone up 5.4 feet, but he's down negative 10.2 feet. So if we add those together, plus 5.4, that gives us a y displacement of negative 4.8 feet. So while he's sailing through the air, right, he's going to go up and back down. When he gets to this spot, he's going to be 4.8 feet down from where he started, but that's still over 5 feet above this thing. So he's going to be up here, and he's still going to make it okay, right? He turned out better than Goober did, right? So hopefully that helps. I know that's fast, but if you're watching those, pause it and try and work ahead of me on those because I have to get these in under 5 minutes for the software to work.